All right, welcome everybody. I'm glad you could make it on such short notice for this workshop. We are trying to, as you know, among all the teams, compute our correction factors for each Blue Sky device so that we can embed those into the TSI Link software or right onto their website. And that way, whenever we look at maps, such as this one here of all of the sensors in our given network, we can be sure that the differences that we're seeing between two sensors, let's say this one in the cantonment and this one near to the airport, are actually reflecting differences in the PM 2.5 levels and not biased by any difference in factory calibration. What do I mean by that? Well, you'll remember last year when all of the teams ran the original Python soft code that did inner comparisons of co-located sensors, that everybody was producing nice graphs like this that showed that just about any pair of sensors of blue sky monitors, when placed next to each other and measuring the PM 2.5 in the lab or in the outdoor environment, had very, very high correlations, like 0.996 was not uncommon. And we saw this over a range of PM 2.5 values. Initially, this was very comforting. We thought, oh, great, these blue sky devices are working awesome. Let's just go ahead and deploy them. But upon closer inspection, if we look at this regression line really closely, we can see that sensor number 5 here is measuring quite a bit higher than sensor number 3, maybe about 15% higher by my eyeball. And so if that's the case, if this sensor, when placed next to each other, if it's measuring 15% higher, then when we deploy it out in the field, a lot of this difference between 42 and 29, a non-negligible amount of this difference can be due to differences in the sensor readings. And so we want to get around that. Now, how are we going to do this? The very best approach would be to write a computer-based script in R or Python, Fortran, MATLAB, whatever, that reads in the data, maybe from your QA'd level 1 data, and then outputs the correction factors for each and every sensor. And then you could share this script with other team members within your group, with other country teams, and then everybody could be able to do derive these correction factors. We've been hoping that one of the teams would be taking the first step in doing this, but it hasn't happened yet over the last couple months. And so today's workshop is to explore how we can achieve this same objective, that is to derive sensor-specific correction factors using basic spreadsheet software. And before I go further on this, I want to warn you that, and you probably know this, that processing large amounts of data in spreadsheets can be very tedious, but more importantly, for our research purposes, it's very prone to errors. It's really easy to misclick something, refer to a wrong cell in a formula in Microsoft Excel or Google Sheets, and that can cause your answers to be completely wrong and difficult to trace those errors. Whereas in a script, such errors are more easily found when somebody else runs the same script, as we're seeing right now with, for example, with Darren's Python code. Everybody's trying to run that same script and bumping into different problems. And we're more likely to catch errors as well as hopefully minimize the tediousness. Okay, so with that introduction, I wanted to say that today's workshop is designed to be interactive. I could have just done a YouTube video on this, but I might be saying things that don't make sense to the group, and that's why I'd like you at any point in time, if you have any questions or anything I'm saying is unclear, to please just unmute yourself and say whatever it is, and I could go over it again or more clearly. I've budgeted an hour for today's workshop. We might go a little bit over time, but if we don't get through all the way to calculating sensor-specific correction factors, that's okay. We can have a follow-up workshop and complete the material. The important thing today is that everybody who's here, and it looks like we've got 5 or 6, oh wow, we got several people from 4 different countries, at least comes away with a clear understanding of how to approach this problem using spreadsheets. So let me pause there and see if there's any questions so far on the motivation or what it is that we're trying to do. Yeah.
No, sir, all good, sir.
Okay, thanks, Sandeep. All right. So we are going to start out with a sample data set. Let's see. Let me stop my PowerPoint. And now is a Microsoft Excel spreadsheet showing on Zoom? No. Okay. Let me stop share and share again. All right, now I think everybody can see my spreadsheet here. Where did I get this spreadsheet? This was the output from Darren's Python code that produced level 0 and level 1 QA data files. And in this case, I've opened the level 1 hourly data file, level 1 hourly.csv, and just open it up in Excel. And it looks something like this. I've also deleted a number of rows from this file. I haven't changed any of the columns, but I've deleted the rows so that I'm just looking at a narrow time period, in this case December 11th through December 19th, which was the period when these 20 sensors, these 20 blue sky monitors, were all co-located in a laboratory. So that was my first step, was taking the level 1 hourly data file and then trimming out the rows that I didn't need for this analysis. Once I have this file, I'm going to make a copy of it. I'll just right click on the tab here, select copy, and this will be the data file where, or this will be the worksheet where I'll do my work. I'll call it Scratch for now. Okay. So again, keeping my motivation in mind and what my objective is, there's a number of columns of this file that I absolutely don't need. The longitude and latitude aren't important because these were co-located in a laboratory. These 20 devices were running at the same place. I don't care right now whether it was indoors or not. I don't need the PM1 values, PM4, PM10, or any of these custom calibration factors. I also don't need the number concentration information that comes out of the QA file, nor do I need to know anything about particle size, temperature, humidity, time delta, entry count. Really don't care about any of that. Just trimming down the data file to something that I can easily work with. Okay. So what I'm going to do now is, if you look at this data file, I'm going to sort it in different ways. Let me sort it by time first, just so you can see what the data look like. These are going from December 11th down to December 19th. And there's a variety, there's 20 different blue sky devices that were making measurements at the same time. Well, what we want to do is to be able to calibrate, or what we're going to call harmonize. We want to harmonize the readings of the PM 2.5 so that at 1800 on this day, all 20 of these numbers should be approximately the same. They're not going to be exactly the same, but after correction, we want them not to vary from 95 to 157, because if these devices were all out in the field at different places, we'd want them to be giving readings that are comparable with one another. So with that goal in mind, what I want to do is I want to reshape this data set so that rather than it being one record per row and 20 rows for every hour, it would be much easier to work with if I could get it so that it was 20 columns of data, one column per Blue Sky device, and then as many rows as there are hours in my data set. And I don't want to do this manually because it'll take a lot of time, and there's a lot of chance of errors, especially if there's time gaps in some sensor readings that aren't in others. And so I'm going to do this using a pivot table. By show of hands in the group here, if you could just do a hand raise if you've used pivot tables before, either in Microsoft Excel or in Google Sheets. They both have pivot tables. I'm going to raise my hand. How do I do that? I'm not allowed to react to myself. Oh, there we go. Okay, Sandeep and I have used pivot tables before. All right, great. So pivot tables are and Hashna has too, good. Pivot tables are really, really useful component or feature in spreadsheets, but very underused. And so let's start by really quickly showing how this pivot table works. So I'm going to first highlight all the columns of my data, and I'm going to go to Insert and choose Pivot Table here. You can see the description. It helps us easily arrange and summarize complex data in a table. I'll select Pivot Table, and the Pivot Table dialog box opens up. It first wants to know where are the raw data that I want to tabulate, and they're in these columns. That's already been done. And then it asks me, where do I want my pivot table to be placed? By default, it wants to put it in a new worksheet, but I want it to put it in this same Scratch worksheet. So I'm going to choose Existing Worksheet, and then in the Location box, I'll click this arrow and say that I want my pivot table to hang out right here, or just to start right here in cell H2. Now I'll click OK, and this icon shows up where I can now build a pivot table. All right. So let me first start by showing you what a pivot table could do. Let's suppose I wanted to make a pivot table that had the serial numbers in every row. So I could do that by clicking serial number and dragging it down to the rows box. And then let's suppose I wanted to know what the average PM 2.5 is from each of those Blue Sky devices. I could click PM 2.5 and drag it over here to the values field. And what Microsoft Excel has done here is it has added up the PM 2.5 values from every row for each device. Well, the sum of PM 2.5 isn't very meaningful, but if I click on this little triangle down here, I can change which field settings I use, and instead of sum, which was the default, I can choose a variety of other ones. I could look at count. I could see how many hours of data are we looking at. Oh, wow, nice. Every device has 198 hours of data. I could also look at the average. What's the average PM 2.5 from each device? And you can see that very handily, Microsoft Excel is doing these calculations for us and summarizing the data in a really easy readable format. So again, the steps to get there were just to highlight the data, go to Insert Pivot Table, and then choose where to place the table. And then from there we could do things like I've just shown. Any questions up to there? That seems pretty easy, right? And like I said, yeah, Cindy?
Yeah, all good, sir. All good.
Okay, thanks. Like I said, this can be done in Google Sheets, as well as Microsoft Excel. Excel is a little bit more advanced in terms of the variety of functions that you can do with your pivot table, but I'm sure Google Sheets will keep catching up. All right. What we want to do is to make a pivot table where the rows are the hours of data and the columns are the different sensors. So how are we going to do that? Well, first, let me get rid of what I have here in the pivot table. So I'll just click on the field, click remove field, click remove field again. And let's see, I want to put my columns that are going to be one for each device. So I want blue sky 2, 3, 4, whatever along the columns. So I'm going to take site name, because serial numbers are a little bit hard to work with. I've got these nice handy site names. I'm going to drag site name into the columns field. And now what I want is I want the rows to be one for every hour. So I'm going to click on timestamp and drag it into the rows field. Okay. So now I've got a two-dimensional table with columns for every device, rows for every hour, but it's empty because I haven't put anything yet into the values field. Well, in my case, I want to know the PM 2.5 from each device and for each hour. And so I just drag that in there into the middle. I'm sorry, into the values field, and I've got, again, by default, it's chosen sum. In this case, it won't make a difference whether it's sum, average, min, or max, because there's only one value per field. I'll go ahead and choose average, just because it makes me feel a little more comfortable. But I know that these are just single values. All right. So far, so good. When pivot tables operate on data on fields that are date and time, by default, it goes in and does some summarizing. So for example, we could see December 11th individual hours, but then also for December 12th, it has the individual hours as well as the all the hours. I don't really like that. I want to check something. So I'm going to right click on, and this part is a little bit experimental. I know how to get around this in a different way, but I'm going to try to do it ungroup. So bear with me here.
So I think that is the 12th hour data, right? 24th hour data. It is not saying 00.
Thank you, Sandeep. Yes. Okay.
That's why it's not happening.
All right. Yeah.
You cannot ungroup that.
So I don't need to. Pardon?
That's why you cannot ungroup that, right? It is completely hourly data only.
Okay, fantastic. So we don't have to do my shortcut. It's already the hourly data, it's not the whole day. Okay, so erase what I just said. Sandeep's right. This is exactly what we want. This is the hourly PM 2.5 data from each of our 20 devices, lined up and tabulated so nicely. We can now operate on this data set. I'll go out. Okay, so great. Now what do we want to do? Our next step is we want to calculate these correction factors for each device. And what do we want to correct them to? Well, we have 20 devices running here side by side. What would be the most robust metric of representing maybe the most accurate PM 2.5 value? We think that the most robust metric is the median across all the hours. And so I'm going to make a new column here, call it median, because the median, as you all know, is not sensitive to outliers. And I'm going to calculate the median of these 20 rows by just using the median formula here. And that's going to be my reference. I'll, oops, go ahead and copy that. And paste it down here. That's my reference. And now what I want to do is calculate how different each of these other devices are from the median. Let's go ahead and do that using, oh yeah, and now here, there's one little nuisance when dealing with pivot tables. They make beautiful reports, but it does tend to be difficult to refer to cells that are within a pivot table. For example, if I just wanted to put my blue sky number 2 data here for this given hour, and I reference this cell, rather than just referencing the cell I4, as I would really like it to do, it's doing this complex query on the data, on the database, using this get pivot data formula. All I did was type equals and clicked on I4, and instead of getting a normal Excel formula, I got this ugly thing. So I'm going to replace that with equals I4. This is part of the tediousness that I warned you about earlier. Once I've done that, I can fill in all of my values, and let me go ahead and do that for all the different devices so that I'm not accidentally referencing some kind of a report query. So so now I've got blue sky 7, 8, 9. Essentially all I'm doing is I'm using the functionality of the pivot table to reshape the data set, but then I'm manually creating a real easy table of data that I can work with. Importantly, and this is just a best practice, I don't recommend copying the values and then using paste special, because then there's no traceability of where did this 165.75 come from. If it's just a paste special value, then there's no way to trace back where it came from. So I do recommend that you still use formulas, but perhaps not the complex formula of get pivot data. All right. Now we are at a stage where we can simply regress any given blue sky value against the median. I'll do that by highlighting, in this case, blue sky 2 versus the median. And then doing what I think almost all of you have done before, inserting a scatter plot. I'll move the scatter plot over to the side, and I'll line up all my scatter plots over there once I get them. When plotting scatter plots, we urge all of our team members to square your axes. So if it's going from 0 to 180 on the y-axis, we want to do the same on the x-axis by double-clicking. And changing the upper limit to 180. It's also really nice if the aspect ratio of your axes are 1 to 1. So these grid boxes, whoops, are roughly squares. All right. Let's add labels to our axes. Make sure that we've got blue sky 0, 2 here on the y-axis, and the median of 20 blue sky markers on the x-axis. I don't need that title. Just want to make my graph really good looking so that once I start to do this over and over again for all my other devices, all the plots look good. Lastly, I'm going to add a regression line. So I right click on the plot area and I left click on the data. Do this again, make sure I'm saying what I'm doing. I'm gonna, instead of clicking on the data, which selects all the data, let me right mouse click on the data and get this menu where I can add a trend line. Pull that over a bit. By default, Excel looked at the data and decided a linear trend line was best here. I want to see what the equation for that trend line is, as well as the r² value. Probably all know this, but Excel does this all quite handily within the scatter plot option. And now I have a slope and intercept for comparing blue sky 2 against the median. Okay, at this point I want to pause and make sure that I didn't go through any of the steps too fast, that everybody thinks that they could create a plot like this from their own level 1 QA data. No questions. Okay, so it's pretty easy. The pivot table was probably the only new part for a few of you. Let's continue then. So we've got, let me make sure something. I've got HE against AF. I am a little bit alarmed by this group of data up here, and to be quite honest, I haven't looked at this exact data set before, so I don't know what is going on with these values up here. I haven't seen this issue in other data sets that I looked at, and so what I'm going to say here is that if you do plot your data and you find a bunch of data that are off center from it, take a look and see if those data come from a particular time period when perhaps the sensors weren't co-located. That would be my guess here. And because in all of the inner comparison plots that we've done before, we had really high R-squared values, nothing as low as 0.8997. And so that makes me a little suspicious that the blue sky, these 20 blue skies weren't all co-located. Maybe number 2 was moved somewhere else. I want us all to make a copy of our scatter plot and then repeat the regression in a way that the regression line goes right through the origin. There would be no intercept, and I'll explain that in a second. So all I did was I selected the entire plot area, Control C for copy, and then moved over here a few cells and pasted it. Now I've got a regression line. Let's see if I can get to it. Yes, okay. So again, select the data, right click on it, add a trend line. By default, Microsoft Excel gave me a linear trend line with a slope and a non-zero intercept. We want to have trend lines with 0 intercepts. So I'm going to go down here and click the box that says set intercept to 0. I want to add that equation as well on the chart. And I'll put it, sure, I'll put it over here. Let me do one more thing. Let me color my my line that has no intercept a little bit different so that I can make it out from the other ones. I'll make it red if I can do that. Yay. Okay, great. So I've got a red line that's going through 0. That's a linear regression line with no intercept. And then I have a blue line that's going wherever it wants. It's showing higher slope and a negative intercept. All right, now we've done, so for this harmonization step, we are going to use the regression with 0 intercept because all of these devices were factory calibrated to measure 0 micrograms per cubic meter when they were delivered with clean filtered air. So we're going to trust the factory calibration at the 0 point. And we're going to go ahead and repeat this for a few more sensors. I won't do all of them, but that'll be an exercise that you would have to go through. Once you have a couple of copies of this, right, this is my original Blue Sky 02, and then down here I just copied and pasted more versions of that. I want to make one for Blue Sky 07 and one chart for Blue Sky 08. So I'll just relabel them so that I know what I want first. And then I have to go in and adjust the data. So I'm going to right click on the data, choose select data here, and then choose edit. And I want this to be Blue Sky 07 compared against the median. So my Y values, instead of AG, they should be AH. Just going to edit them. Leave the X values as they are because that is our reference. That's the median across all 20 sensors. And let's see, one more nuance about this is when you're in these windows, you don't want to click any of the arrows. You don't want to move your cursor around using the arrows because that changes the formula entirely. So you do have to navigate this with your mouse in order to get a meaningful formula in here, or a meaningful reference to cells. All right, I've done that. I clicked OK. I got my Blue Sky 07 data here, and I want to do one more time. Blue Sky 08. Again, I'm right clicking on the data points, clicking select data, choosing edit, and then changing, in this case, okay, instead of AG now, I want AI. Say okay, and then go back over here. And now I have three different regressions for three different devices. What do we see just by looking at these first two? That Blue Sky 2 was measuring 5%, 5.4% higher than the median. Blue Sky 7 was 8% lower than the median. Blue Sky 8 is 30% higher than the median. Wow. One thing that I'm really happy about is that Blue Sky 8 doesn't have any values off the line, so I really like Blue Sky 8. It's behaving really, really well compared to, hey Tamim, compared to all the other values, sorry, all the other, the median, which is our reference. So I mentioned at the outset that this is a tedious process doing this for many, many sensors. And that's why it would be ideal to do this coded in a script in R and Python. But it is possible to do it in Excel, and that's why I decided to have this workshop today. Now, so is everybody okay? I know we had a couple join late, but it's all, I think it's all recorded. Does anybody have any questions about how to get these equations right here? The regression line through all the data points with no intercept. Or any questions about anything up to this point?
Excuse me, sir.
Yes.
Yeah, we are working on the data set that is during the collocation time, no, sir?
That's correct. Yes, good question. The first step I did was I took my level 1 hourly values that came from the Darren script, and I deleted all the rows that were outside of the collocation time period. So in this case, I know that these devices were collocated from December 11 to December 19, and I deleted all the other rows, December 20 onward, and everything before December 11th. Those are all gone. Then I made a copy of that and put it in the Scratch, and that's where I started working from, was this reduced data size. Other questions?
Sir, I have a question actually. More than a question, actually, I have an observation on level 1 data. Like, I think these are the sensors from Kanpur only, right?
No, these actually are from the lab in Dhaka.
Okay, all right. So, okay, within lab, we are seeing so much of variance within these sensors.
Yes, yeah, that's right.
Okay, right.
Within the lab,
Actually,
the balcony.
right, sir.
Yeah.
So actually, I was trying to figure out one thing. Like, since this is level 1 data, this is clean data set, right, sir? We have removed all the negative values, and we have
Above
done all the cleaning,
1,000.
data cleaning, right? Right, above
Yeah,
1,000, and right, we are trying to remove the outliers also by keeping the values above 1,000 as 1,000, capping that, right, sir?
correct.
So actually, what changes, I mean, what observations even I was seeing in level 1 data is that at certain point our reference monitor is giving good data. It is like 60, 70, but since we have capped it to 1,000, it is showing the value as 1,000. So is this correct way of cleaning the entire data set at level 1? Because this is definitely increasing the mean in that period for that particular point. And that has also increased or decreased our slope and intercept also.
Increased. Okay, so values above 1,000 get capped at 1,000, but we shouldn't be increasing any values in the level 1 QA. Maybe I misunderstood you. So
No, my question is like, sir, when I checked it with the reference monitor at that specific point, for example, our sensor was showing data like 1200, but we are capping it to 1000, right?
yeah,
But our reference monitor was showing for that particular time, data was hardly like 200 microgram or 70 or 80. So what I see is that particular data in Blue Sky sensor is actually an anomaly. Actually, it's not the right data. So we need to remove that data too. So instead, right, and not just 1000 in fact, not just like capping the values above 1000. Sometimes I'm also getting the value like 700 or 800, and while the value of the reference monitor is less than 100 in fact. So I think we need to check on that data also. And in fact, possibly this is one of the reasons we are seeing these outliers here in level
okay.
1 data.
Yeah. Okay. Thank you, Sandeep, for pointing that out. So what Sandeep is describing is actually the second step of the calibration, which is calibrating your. So we're dividing our calibration into two steps. First is we're trying to harmonize. We're calling it harmonizing. That's not an official term, but we're just going to call it that for our project. We're harmonizing the values from all sensors so that if they were co-located, the Blue Sky values would match with the other Blue Sky devices. In this case, for example, Blue Sky 8 is measuring 30% higher than the median of that cluster of sensors, even though they're all in the same place. So our first step is we want to cut down the Blue Sky 8 values by 30%. Before we do any calibration with it, before we compare it against a reference monitor. We learned this the hard way by working with IIT Kanpur team, where different sets of sensors were calibrated against a reference monitor at different times. So Sandeep, what you're talking about is definitely outside of the scope of today's workshop, because we just want to make sure our Blue Sky values match up with the other Blue Sky values.
Got it.
Okay. Now, okay, so now we have correction factors. Now, well, we don't have correction factors yet. We just have a slope of Blue Sky versus a reference. I'm going to take this sensor number 8 as an example because I just like the data here. They look really good to me. And I see that the slope here is 1.3015. Great R squared value. So really good agreement between Blue Sky 8 and the median of 20 co-located samplers. So what I want to do, as I mentioned earlier, is I want to have Blue Sky 8 not be measuring 30% higher than all the other sensors. I want it to measure almost exactly the same as the rest of the sensors. So I'm gonna put here. I'm going to calculate my harmonization factor. What is the harmonization factor? That's the factor by which I'm going to multiply Blue Sky 8 values so that they match with the reference. In this case, the reference being the median of the 20 samplers. Well, that's just the reciprocal of the slope. So I need to set an equation here. Let's type equals 1 divided by this 1.3015. And I jumped over one detail. Well, how much precision do we want in this slope? Let's go ahead and stick with 4 decimal values. It's overkill, I know. It's way more precision than the precision of the instrument. But we're going to be doing a number of subsequent calculations, so we don't want to round off too early and then have a propagation of error through our process here. So we're going to go ahead with 4 decimal points on the slope, and then on our harmonization factor, that would then be accurate to 3 decimal places, and we'll start losing precision as this goes along. So for now, we have then a harmonization factor of 0.768, and this is the value that all of my Blue Sky 8 data should be multiplied by in order to eliminate biases in the factory calibration of that sampler. What do I do with this number? I go to TSI link, and when I'm logged in as the owner of one of the devices, I'll click on the device tab and find the ones that I own, which are only at Duke. Here, let's pretend that Duke 1 is this device, Blue Sky 08. It's not, but let's just pretend, because I've just calculated a harmonization factor for that device, 0.768. I'm going to go over to Duke 1, click on the 3 dots here, and in settings, I'm going to choose calibration and set the multiplication factor on PM 2.5 to be 0.768. And why? Ooh, interesting. I didn't notice that before. Calibration factors can only be 2 decimal places. The default value is 1 with no calibration applied. So 0.768, TSI allows me to make that only as precise as 0.77. And then I'll click the Save button. And then from there forward, all the values that are coming from Duke 1 are going to be not from there forward. These calibration factors are applied for, back in time as well. Now, all of these values have been dropped by a factor of 0.77. If I go to Export CSV, I can look at my last week of data. As I think many of you have done this before. And when I open this file now, one thing should change, I hope, if I've done this right. And it hasn't happened. Okay. Over here, I was expecting to see that custom calibration setting of 0.77 show up in my file. It doesn't appear to have shown up, and so that's something I need to report back to TSI. But this is what we want to get to, is calculating these harmonization factors for each and every device. I'm going to show an example of what we'd like the output of this exercise to look like. This is something that was been done in our Bangladesh team by another collaborator. What we ultimately want is a list of each of your devices, the start and end period of the co-location, and then what that harmonization factor would look like. So that number. This is what we want documented from each group. So in my case, I've got Blue Sky 08. I did December 12th through the 19th, and my harmonization factor is 0.768. It's 1 over the slope of the regression line. And we want to tabulate this for each and every one. We want the start, the end period, and the harmonization factor for all of the devices, Blue Sky 02, 7, and so forth. Whoops. What am I doing? Okay. in all of the countries, the sensors were shipped in multiple packages. Like many of you got 6 sensors the first time, and then a bunch more the second time. And I think in Bangladesh you got 3 sets of sensors. And so your co-location period might vary. I think in Nepal you had about 7 or 8 sensors being placed side by side. And so the co-location period for those would be different from the next batch of sensors. So you'd have, that's why it's important to tabulate the start and end, so we know when what time period the harmonization factors were derived from. If you would do this for I would suggest doing this with your largest group of sensors first. So if you had one period when 6 sensors were co-located and another one where 20 were co-located and then a third one where 50 of them were co-located, I would choose the one with 50 for this exercise to start with, because that median of those 50 samplers is going to be the most robust value that we could possibly get from the blue sky sensors. So this median here, for example, would be the median of all 50. And then in our individual team meetings, when we meet with you, with your country team, we can talk about how to take that corrected value and then use it to calibrate the smaller clusters of sensors. So again, start with the biggest cluster, calculate its median, compute these scaling factors for each of the sensors within that group of devices, and then tabulate your harmonization factors as I've done here, along with the start and end times. And then we'll be at a stage where we can plug those into TSI Lake once that feature is working, and be able to just look at maps and know that there's no sensor-to-sensor disparities that are driving differences in PM2.5 between the data. That'll also enable us to do a more meaningful calibration against a reference monitor when we get to that stage, which is what Sandeep was at, as well as hotspot analyses, and then the other fun stuff that we want to do with the data. I'm going to stop my share and see if there's any questions today about the pivot table, or what the exercise is for calculating the slope of the regression line in order to get the harmonization factors. And if everybody wants to turn on their video, we can all say hi to each other too. I'm going to pause the recording now, and we'll restart it when there's some questions of technical importance.
Based on keeping it, after keeping intercept as 0, right? So we are trying to nullify the effect of intercept, and only trying to change by keeping that harmonization factor for slope only, right? So yeah. So question is like, what if we do like in our last meeting, our personal meeting, we found the correction factor based on both intercept and slope for each sensor with respect to the mean of all the sensors. Let us keep it as median. But what if we get both the values of intercept and slope? How different will it be based on both the factors, as well as or with the only keeping slope as the harmonizing factor?
Okay, great question. Yeah. In this data set, let's see. Okay, let me answer your question with this example. So share the screen. All right. So here's Blue Sky 8, right? This was a well-behaved sampler. We calculated this slope as 1.3015. If we had, in the case where we allowed the linear regression line to not go through the origin, to let the intercept be a free variable, we got a really similar slope, but we got an intercept of 0.4742. Mike and I talked about this, and we decided that this intercept is actually smaller than this is 0.47 micrograms per cubic meter. That's smaller than the detection limit of the device itself. And typically in our environmental sciences, if something is within 2 or 3 times the detection limit from 0, it's customary to neglect it. And so we want to look at what that slope and intercept is. That's why I did it both ways, right? We have both regressions here on the plot. And we want to first verify that that intercept is indeed small, within plus or minus 2, or maybe 2.5, maybe 3 micrograms per cubic meter. If it's more than that, then we need to inspect what is going on with that device. Like, for example, this is troublesome to me, this Blue Sky 2. Why does it have a slope, an intercept that's more than 6 micrograms off the median? Probably because this cluster of data, there's something wrong with it. This wasn't truly co-located. I don't want to blindly use this 1.05 correction factor, or the reciprocal of this is my harmonization factor, until I've understood why this intercept is so off from 0. Once I get a result where my intercept is small, then I want to eliminate the intercept, force the line through 0, and then use this. So in your case, you already did the regressions and you got non-zero intercepts when comparing one Blue Sky with another. I would say we should go back and look at those like I've shown here and see, well, is that non-zero value really significant relative to the detection limit of the device? And if it is, let's look again at the value. Let's look at the data more carefully, because it shouldn't be. It shouldn't be. I think I've looked at a bunch of data from Sri Lanka also, and we got plots very, very similar to this for all their devices for their first 6 devices. Then I looked at another 6, and they were all over the place, and that makes me think that the devices weren't actually co-located during the time when they said they were, or maybe one of them was malfunctioning, because 3 of the devices went very close, like lined up perfectly with each other, and then 3 of them were a little bit off. Well, that really shouldn't happen. It doesn't jive with what we saw in the very first intercomparison exercise. So I hope that answers that question. That's a really important question, and something that we've thought about a lot. We do want our scaling factors to be without intercept. It makes the math a lot easier. As we've seen, like, once you have an intercept, you have to do some more mathematical acrobatics to get your corrected values, and then when you're trying to correct another set of sensors off of that one, very prone to error. So this seemed to be the straightforward and defensible way to go.
Right, sir. I'll check with that.
Any other questions before we sign off for today? All right, well, thank you all for attending. Oh, yeah, go ahead, Hashna.
So maybe it's a simple question, but I'm getting confused. Just like the percentage you are mentioning over here, with what comparison it's the percentage?
Okay, yeah, good question. This 15% higher, so in this plot, I don't have the slope, but I'm just saying that sensor 5 is measuring about 15% higher than sensor 3. Because sensor 5 is around 45, 46 micrograms per cubic meter, and sensor 3 was 30, 37 or 38 or something. So that's where this 15% is really rough, but basically the slope is above 1. If I had the slope plotted on here, the slope would be like 1.15 or something.
Okay, sir.
Yeah. No. Yeah, there's no dumb questions. I bet if you have a question, probably somebody else has the same question. So please, yeah, go ahead and ask. Okay, so then let me see if my objective was met. Does everybody think that they could, if you haven't already come up with your own way of getting your calibration vectors, do you think you could follow this approach and compute yours?
Sure, sir.
Okay, let's give it a try, and then when we meet next time, we'd love to look at your results. If you have run into any problems along the way, post them in Slack. Feel free to post your results in Slack too. I think this will motivate some of the other groups to get past this hurdle. This has been a hurdle for many of the groups, so we want to get over it for everybody.